really in the front, the details of each lecture, the program broken down on a weekly basis, and also the way that we're going to be evaluating the course. So basically, we have a midterm schedule, which counts for 35% of the grade, and then there's a final exam based on all the material at the end, which is 45%, and the remaining 20% is a tutorial grade. Now the tutorial, how we're going to calculate the tutorials, you'll see I've just issued you with a tutorial, the first tutorial. Every week I'm going to have a tutorial, and I'm going to post this on the Ilium website from now on. So I'm going to create a website for this course so you can download lecture material, also the tutorials and other pertinent information, also grades and stuff like that. And basically I'm going to give you a week to do this. So you'll get it on first thing on a Monday morning. You can download it or I'll print it out. And it will be due then at the end of the lecture, Mondays. So when you leave the class, just drop it off here. And if you can't make the lecture, then just give it in the Monday tutorial session. So, and how that's going to work is, I think this is very important because this is a very dense course. The information is very compressed. So I think it's important that we try and stay on top of the material by doing these tutorials. And we're going to grade these and give you feedback on it. And based on the tutorials, we're going to give you a grade out of 20, right? So, morning. And there's going to be 5 tutorials, and we'll pick the top 4. So that will give you a grade out of 20. So this is very, very important. It enables you to stay on top of things. You get some feedback. And I think that's how we're going to do that. The midterm is scheduled for, it's in the course manual. It is Monday the 29th of February, so basically a month from now. And I think it's a month, yes, it's Monday 11 to 1, so it's a 2-hour session. It will be based on the first 3 lectures and associated PBL sessions, so that's very important. The next thing is the textbook. This is the textbook. It's a very big textbook. One of the advantages of having this textbook is you don't need to join the gym because you can use this for exercising. So it should be available at most bookstores. You can certainly purchase it online, and I suspect it might even be available at Aperture. I used this textbook last semester for students at UCM, and they didn't have any problems finding it. So you will certainly be able to find it. The final exam is scheduled will be on all the material, everything. So this is a 6-week course, so it's very, very dense, very compressed, and you've really got to stay on top of things, right? So that's very important. Finally, the PBL sessions, which in fact start today. I just want to, let's just go there, if I can actually close this for a moment. So here we have a breakdown of the, well, here you can see that the final exam is scheduled for the 21st of March, Monday, all right? From 8:30 till 10:30. So that's, just make a note of that. And of course, during the course, I'll remind you. And here are the tutorial groups. So there's 2 groups. There's my group, which meets group 1, which meets straight after the lecture, from 11 till 1. It should be in your schedules. So maybe you can just see if you're in my group and make a note of it. And the second group meets today, if you look at the schedule, from 1:30 until 3:30 with Fabrice. And maybe you can just make a note of that if you haven't already. That's his group. The PBL sessions are very important, and the contents thereof will also be examined. So it's not just the contents of the lecture. Speaking of the contents of the lecture, I will be posting the lecture every week on Ilium, so you can use that for evaluation or for helping you when you're preparing for the midterm. I think that's all. I mean, the rest of the issues we will discuss as the course goes along. I haven't actually introduced myself. My name is Birgit Blom. You can call me Birgit. And I have an open door policy. So if you don't understand something, please just come over, right? Or make an appointment. I want you to feel comfortable to do that. That's very important. And yeah, don't be scared to ask questions. And yeah, I think the rest of it we will just figure it out as we go along. All right, and I realize this is all new for many of you. It's the first time you're doing this. Don't be scared. I think everything will work out. Okay, so now let's move on to the actual course and what the expectations are. As I said, this is a very compressed and dense version of chemistry, squeezed into 6 weeks. We are aiming to give you just the basic tools to pursue further chemistry courses in the fall semester and later on if you develop an interest in chemistry, but also to give you the basic tools to pursue other things like molecular biology, genetics, microbiology, and even physics. Chemistry is a very important central science, and having at least some understanding of it is very important. That's why it's one of the core courses here in the program. So that's the goal. And yeah, I think what we should do now is actually sort of shoot straight into it. You will notice that these lectures are very, very dense with information, extremely dense. And we move very quickly. And that's why I'm going to post the tutorials online. I mean, the lectures will be posted online, the actual PowerPoint slides that you can afterwards, when you've caught your breath, actually just go and refresh yourself. So, are there any questions? All right. So what's on the program for today is quite a lot. We're going to discuss atoms, quantum numbers, and molecular geometry, and Lewis structures. So this is a very important cornerstone of basic chemistry. Incidentally, that's my office over there in Kuhlenstraat 14, 2002, so on the 2nd floor. And this is my email address. Anyway, it's all in the course manual. All right, so really the starting point is, of course, the periodic table. And I assume most of you have seen something like this from high school, at least I hope so. And the periodic table is divided essentially into groups which run from top to bottom and periods which run from left to right. And you will notice in this periodic table, we've got basically 2 sets of numbers here for the groups, one above and one below. Now these are actually just different numbering conventions. For the purposes of this course, the important one is the bottom row. That's sort of, you will see why in a moment when we're talking about drawing Lewis structures. So I want you to stick to the numbering convention at the bottom here. Now the periodic table is essentially divided into blocks. So groups 1 and 2 is called the S block. And we will see why in a moment. We call that the S block elements. We have these from basically group 3B here to across here. This block here is the so-called transition metals, the D block. This over here, so this block here, this entire block here, so groups 13 through 18 are the so-called P block elements. And at the bottom here, these strange elements are the F block elements, the lanthanides and the actinides. Now, groups 1 and 2, so these elements here and these elements here, so 3 through 8, using the numbering convention at the bottom, we call main group elements. And quite honestly, for the purposes of this course, we're going to essentially focus almost exclusively on these, except in the last lecture, we're going to discuss a little bit about the transition metals. But for the moment, the important elements are the main group elements, groups 1 and 2, and groups 3 through 8. The way that this periodic table is built up is defined by the electronic structure of the atom. Now, we don't just put electrons willy-nilly into atoms. There's a very specific way that we do it. And there's a very well-defined structure for an atom in terms of how the electrons are filled up, and that's what we're going to look at in a moment. And the electronic structure essentially puts the elements in a certain position in the periodic table. So the way that the electronic structure of an atom is defined is really, comes from quantum mechanics. quantum theory, which is physics. It's the physics of the very small, not classical physics, which is the physics of the very large, because of course electrons are very small. And actually chemistry really is a science of valence electrons. The chemical reactivity of an element is dictated by its electronic structure. And we can sort of think of electrons in an atom as being defined by 4 quantum numbers. The principal quantum number, the orbital angular momentum quantum number, magnetic quantum number, and spin quantum number. Now the way to think about these 4 quantum numbers, it's kind of like if you send a postcard to someone. You write an address. You write the street, you write the street number, you write the city, and you write the country, right? And you put that in the post and it arrives somewhere. But you need the house number, the street number, the city, and the country. Otherwise, the postcard is not going to get where it should go. And that's exactly what these quantum numbers are. They tell us where in the atom the electron is found. Right? Now, we're going to start off with the principal quantum number, which is sort of like the country, you know? Where in the atom are we? And the principal quantum number is basically, we define it by a value n. It has values 1, 2, 3, 4, in fact, up to infinity. And it's really the probable distance from the nucleus where you're going to find an electron. Another way of thinking about it is it's basically a principal energy level, okay? And it has permitted values from 1 up to infinity. Of course, we don't have so many electrons, so it doesn't really go up to infinity in practice. But according to the laws of quantum mechanics, it's possible to go up to infinity. Now here at the bottom, you see actually, this is an energy diagram showing the principal energy levels. Okay? Now you see here we've got 3. Now there's a specific way that the electrons are filled up in these energy levels. And you will see here at the bottom, we've got a 1s, and in n equals 2, the second energy level, 2s and 2p, and in the third energy level, s, p, and d. Now, those come from the second quantum number, which is called the angular momentum quantum number, or the orbital angular momentum quantum number. And in each energy level, n, we have a certain permissible array of values for the orbital angular quantum, orbital angular momentum quantum number. So, in the first energy level, we are only allowed to have L equals 0. In the second energy level, L can be 0 or 1. Third principal quantum number, in other words, the third energy level, or principal energy level, 0, 1, and 2, and so on. So basically, the orbital angular momentum quantum number for a specific energy level, n, can be any value of n minus 1. So if we, in the fifth, if n equals 5, in other words, in the fifth principal energy level, L can be 0, 1, 2, 3, or 4. Now these values each correspond to a specific subshell time, or orbital time. So if L equals 0, it corresponds to an s subshell, or an s orbital, we call it. If L equals 1, it's p subshell, 2, d, 3f, and so on. Now these names come from physics, actually. Here you can see at the bottom, sharp principle, diffuse, and fundamental. And what these things are, these orbital angular momentum quantum numbers actually reflect orbitals. Now these different orbitals, or subshell types, have different shapes. But before we get to the shapes, we have another quantum number, which is the magnetic quantum number. So to come back to my analogy about the address, the principal quantum number is kind of like the country. The orbital angular momentum is kind of like the city, right? So we're getting, we're defining an electron in an atom. Third quantum number is the magnetic quantum number, and this is sort of like the street, right, of the city, to use that analogy. Now this quantum number depends on L. So it has permissible values from minus L to L, including 0. And this quantum number tells us the number of possible orientations in space of a certain subshell time. So if L equals 0, we're talking about an S subshell type. the allowed ML values for that subshell type is what? 0. Only 0. Meaning, it only has one orientation in space. In other words, there's only one s orbital. What about if I have L equals 1? L equals 1 corresponds to a p subshell type. So how many ML values would I have for that? 3, yeah. Because according to the rule, as we see here, I can go from -1 to +1 including 0. So the possible ML values for a p subshell type is -1, 0, +1. Meaning that there are in fact 3 orientations of this subshell type in space. In other words, 3 p orbitals. So now let's consider a d orbital. A d orbital has an angular momentum quantum number of 2. How many orientations in space would it have? 5, yes. -2, ±2, ±1, and 0 is 5. That means that there are 5 d orbitals, basically. 5 different orientations of that subshell type are possible, and so on. Now remember, don't forget that this is like the street. So the principal quantum number is the country, the angular momentum quantum number is the city, and this is now the street. So, right? So some cities, not all cities have the same street, and don't forget that. So that's a very valuable analogy. The final quantum number we have is called the so-called spin quantum number, or electron spin quantum number. And scientists have basically, by experiment, shown that there's only 2 possible values, plus or minus a half. Now this is, the reason why it's plus and minus a half comes from quantum mechanics. I'm not really going to get into that, but you can think of it essentially as being spin up and spin down, right? So you can think of a rotating ball, which is an electron, spinning around will generate a magnetic field, and depending on the orientation of that rotation, if it's clockwise or anti-clockwise, we're going to get a different magnetic field. The one will be spin up, the other will be spin down, plus and minus a half. Now, the rule here is that each of those orientations I just discussed, in other words, the magnetic quantum number, can have a maximum of 2 of these within it. So, in other words, every orbital can have 2 electrons. One spin up, one spin down. And that's basically the story. Here we have something called the very important experiment, the Stern-Gerlach experiment, 1920. So all of this quantum physics was done in the early part of the 20th century. What they basically did is they bombarded a stream of silver atoms through a magnet, charged silver atoms, and found through a magnetic field that they only collected 2 bands on this detector. And what this basically proved is that the spin is quantized. In other words, it's either spin up or spin down. You don't have a range of spin values, there's only 2. So spin, or the spin quantum number, is quantized, it's discrete, it only has 2 values. So those are the 4 quantum numbers. And if we now look at sort of a picture of this sort of contains all the information we've just discussed. We have the principal quantum number, which is the distance from the nucleus, or the principal energy level. If n equals 1, we can only have an s orbital because we only have one possible L value. And for that L value, L equals 0, we only have one ML value, 0, so only one s orbital. In the second energy level, we have an S and a P. In the third, S, P, and D, and so on. And you see here these lines represent essentially the number of ML values, in other words, the number of orientations of each subshell type in space. And each of these can accommodate 2 electrons from Pauli's exclusion principle, spin up and spin down, right? Are there any questions? Any questions? Anything at all? All right. Please stop me if you don't understand something. One further issue, this is just sort of semantics, if you will, or definitions. These orbitals in an atom tend to be, well, they are on the same energy level. For example, these 3 are on the same energy level. So are these 5 orbitals here, we call them degenerates. So if orbitals have the same energy, they are called degenerates. Degenerate orbitals. All right. Now let's look at the shapes of these orbitals. Now what I want to say here is I find many students confuse or don't really understand the notion of an orbital. The name is actually very misleading. An orbital makes it sound like you have an electron whizzing around on a predefined path, like a planet around the sun. But that's not the case at all. What an orbital is, it's something a little bit more complex. It's really, the answer to understanding an orbital is that it's a probabilistic region in space where you're going to find an electron, or where the probability of finding an electron is high. We draw them as closed spheres, but remember, it is actually probability. And the reason why it's based on probability is because of this equation at the bottom here. I don't expect you to know this, but this is just to show you it's a solution, a so-called wave function, to something called the Schrödinger equation. And it is a very complex function which has a radial and an angular component, and it can get quite complicated. Like here you have the wave function for an s orbital, and here for a 1s orbital, and here's a 2s orbital, and it's even more complicated for p orbitals, and really for d orbitals it's extremely complicated. But the point is that these wave functions here are solutions to the Schrödinger equation, which is an equation which comes from an Austrian physicist, Erwin Schrödinger, and it really, if you like, tells you about the electron in an atom. And the solution to that equation, it's a differential equation, is a wave function. And if we now take this wave function, which is a function, it's a solution to the Schrödinger equation, and we plot it as a function as a function of r, the square of the wave function, in fact, we get a probability distribution. And if we plot that in three-dimensional space, we basically get something that looks like this. So this is a probability plot of these orbitals, the square modulus of the wave function. And instead of drawing dots, it's just too time-consuming, we just draw circles. But remember, it is probabilistic. It is not actually an orbital with the electron whizzing around. It is really a probabilistic region in space where we can find the electron. So here, for example, you see such a plot for a 1s orbital. This is for a 2s, and this is for a 3s orbital. We can do the same for p, d, and f orbitals. All right. This is the same thing for a p orbital. So again, we take the wave function, which is a solution to this hair-raising Schrödinger equation, plot it as a function of r from distance from the nucleus. We get something that looks like that. Basically, if you plot it in three-dimensional space, you get a probability plot which looks like that. And instead of drawing all these dots, which would be more accurate because it's probability, we just draw these lobes here. So here we have the 3p orbitals. Why do we have 3p orbitals? Because the angular momentum associated with the p orbital or p subshell type is what? It's L equals 1. And if L equals 1, ML can be -1, +1, or 0. So there's 3 orientations of this subshell type in space, and one is orientated on the x-axis, one on the y, and one on the z-axis. And that's what they look like. The d orbitals have an angular momentum quantum number, as we just saw, of 2 associated with them. So if L equals 2, what is M? How many different orientations of L equals 2 can we have in space? 5. ML equals ±2, ±1, and 0. And if we do exactly what we did here, take the wave function associated with the d orbital, plot the square modulus. It should actually be in square because we can only have positive values. So the square modulus of the wave function, we get the same sort of thing, a probability plot, and this is what the d orbitals look like. Now, the reason why these lobes have different colors here, I don't want to get too technical, but it's because the wave function upon which these orbitals are based have different amplitudes, a plus and a minus. So yeah, that's the amplitude or the phase, if you will, of the wave function. Okay, you'll see this d orbital over here. This is probably one of my favorite orbitals. It's basically, it looks like kind of like a p orbital with like a torus around it. And this orbital is actually very important in transition metal chemistry, which is not something we're going to discuss in this course. But at this stage, I want you to just be really familiar with what these orbitals look like, and also their names, right? So I think that's very important. And at the bottom of the periodic table, we have the actinides and the lanthanides, and these are the F orbitals, which are very, very interesting. They have very interesting shapes. One very, very rarely in chemistry works with these. This is really something for specialists working with actinides and lanthanides, but appreciate the complexity of these orbitals. Yeah, so I haven't indicated the amplitude of the wave here, but again, all of these orbitals have a plus and a minus, except for the S, which has just got one phase, right? So again, there are 7 of these. There are 7 of these because for an F subshell type, L equals 3, and if L equals 3, ML, the number of orientations in space, the magnetic quantum number can have how many orientations? 7, plus or minus 3, plus or minus 2, plus or minus 1 and 0, and that's why we have 7. So you see, it all sort of fits together. Okay, now, how do we fill the electrons up in an atom? Well, we take these quantum numbers and we use them, and there's a specific order in which we fill up the electrons in an atom, and basically it's shown here. So, of course, we go energy level by energy level, but when we get to higher energy levels, things start getting a bit complicated. So for example, this is very useful. So we first fill up the 1s orbital, then the 2s, then the 2p, going down, then 3s, then 3p, then 4s, and then 3d. So you see, we fill up actually the 4s orbital before we fill up we start filling the 3d orbital, and that's because, you know, although this is in the formally in the 4th energy level, the 3D orbitals are actually lower in energy than the 4s. So you don't fill it up energy level by energy level necessarily, but you have to bear in mind that some of these orbitals have, although they're in lower energy levels, actually have lower energy than some orbitals. They'll have lower energy than some orbitals than you would expect. And this is a result that has been determined experimentally, right? So this order of filling up the atom comes from experimental data. So you can see you go 3D and then you go 4p and then 5s. Again, there I'm filling up adding electrons to the 5s orbital before I get to the 3D to the 4d. So again, you see it gets very complicated, particularly when you start dealing with F orbitals. Yes?
Because the 4D is a lower energy level?
Yes, yes. So you go 4p, no, the 5s is lower. So 4p, then 5s, then 4d. So the 5s is lower in energy than 4d. By the same token, you go from 4d to 5p, then to 6s, and then over to 4f. So it gets, and it's because the energies of the orbitals are not necessarily dependent on the principal quantum number. In other words, the distance from the nucleus. Yes.
Is there a simple method to get the energy?
A simple way of getting it.
Yeah. So you can, get it easier.
Well, actually, this is probably the easiest way to do it. It's quite simple. All you do is you just write 1, 2, 3, 4, 5, 6, 7, and then you have S, P, D, and F, and then you just draw arrows through it. And that's the easiest way to remind yourself of how to do it. And this is important, right? This is something that I would expect you to be able to do, as you will see from the first tutorial. All right. So, as I said earlier, we have a spin quantum number, which can be plus and minus a half. So for each of these orientations in space, in other words, for each of these orbitals, they can have 2 electrons, spin up and spin down, plus and minus a half. And that we call the Pauli exclusion principle. And essentially there's all sorts of different formulations of the Pauli exclusion principle. What it boils down to is that no two electrons in an atom can have the same set of quantum numbers, meaning that you can have some, in an orbital, another way of formulating it is in every orbital there can only be two electrons, one spin up, one spin down. But you can't have two electrons both being spin up, for example, in the same orbital, or spin down. And that is the Pauli exclusion principle. The other important principle when we're filling up atoms is the so-called Hund's rule. So all these Germans that were doing this, chemistry, the Germans really like, they have a tradition of quantum mechanics. Hund, which by the way in German means dog, Hund is a very unfortunate name to have. But anyway, he actually found that when you're filling up, for example, p orbitals, which are degenerate, so there's three p orbitals that have the same energy, each of the p orbitals will first get one electron, and so each will get one electron, and then, say you've got 4 electrons, the first will get the second electron. So you don't put 2 electrons in an orbital, right? Unless it's in a certain energy level. We'll look at some examples in a moment. Here we have the electron configuration of some elements. Notice if we look at nitrogen, for example, how it's filled up. So we have 1s2, 2s2, and then this is over here Hund's rule. So each p orbital gets 1 electron. Do you see that? Of the same spin, right? So it's also called the rule of maximum spin multiplicity. Each gets 1 spin. And then if we look at oxygen, by Hund's rule, this orbital, this px orbital, will get the second electron. So that's how we fill it up. Each p gets 1, and then each p gets the second one. That's Hund's rule over there. You can see that quite clearly. Now, this is something very important, and you should really practice this. There's lots of practice examples in the first tutorial, so really to wrap your head around this. How to write the electron configuration of atoms and ions and charged species. So I want us to do an example together. I want us to do an example of how to write electron configuration, and I want us to do also an example, briefly, of quantum numbers. All right, so let's take an example. Suppose I want you to write the electron configuration of vanadium 3+. Right, how do we proceed? Any ideas? Vanadium.
We have to know the atomic number first.
We have to know the atomic number, and in order, exactly, so to know the atomic number, we have to go to the periodic table. Here's a periodic table, and where is vanadium? Vanadium is sitting over here. I just said that we're not going to be doing transition metals, and now we're doing, anyway, this is just to illustrate an example. All right, there's vanadium over there. It has an atomic number of 23. What does that mean? Means that there are 23 protons in the nucleus, and in a neutral vanadium atom, how many electrons will there be?
23.
Right. But do we have a neutral vanadium atom? No. We have a charged vanadium atom, 3+. So how many electrons will we have? 20. 20, exactly. So we have 20 electrons. And now we are going to write down the electron configuration. And how do we do that? Well, we look at this diagram I just showed you, which shows the order in which the electrons are being filled up. So you can see we first go 1s, 2s, 2p, 3s, 3p, 4s, 3d. All right? And we fill them in. Each orbital can have 2 electrons. So let's do it. So the first energy level only has an s orbital. Remember, because n equals 1, and if in the first energy level, if n equals 1, L is 0, and there's only one orientation of that orbital in space. Second energy level has S and P. Now, according to Pauli's exclusion principle, each orbital can take 2 electrons. So it's 2s2 And 2p, how many electrons can I put in all the p orbitals? 6. I've got 3 of them, each can take 2, so it's 2p6. What comes next? What comes next? 3s, 2. What comes next? 3p6. So we must keep accounts here. We've got with 18, yeah? And then 4s2. That is incidentally why vanadium plus 3 is a stable oxidation state for vanadium. Because you can see that if it were vanadium 2 plus, I'd have 2 electrons in the, or some electrons in the d orbital, but now you see it's what we call a closed shell electron configuration. Alright, so that's basically that. I mean, practice this. This is very important. This is the electron configuration, the so-called electron, we write it out. Another way of doing it is a so-called Aufbau diagram. What is an Aufbau diagram? What means Aufbau? To build up. It's German. Aufbauen. And so another way of doing this is we can actually draw it. So this is the electron configuration. But we also have an Aufbau diagram. And then we can actually draw the energy levels. And somehow that's more satisfying to actually draw it. So we have energy, 1, 2, and 3. And we have 1, 2, 3. So this is actually sort of a picture of what it would look like. These are the 3d orbitals, and this is 4s. So you see the 3d is a bit higher in energy than the 4s, if we look at it pictorially in terms of an Aufbau diagram. Now, I've drawn here deliberately the p orbitals slightly higher in energy than the s orbitals. Actually, for light atoms, they have the same energy. But anyway, I've done this deliberately just so that it helps you in terms of actually the filling order of the atom. So in this case, it would be something like this. You use a half an arrow to represent an electron. Something like that. So you see here, perhaps even better, that the 4s gets populated with electrons before the 3d, and so on. And that we call an Aufbau diagram, because we're building something up. Okay, so that's sort of like how we deal with electron configurations. The next thing I want to just briefly maybe look at by way of example is quantum numbers. So I'm going to write down a set of quantum numbers, and I want you to tell me if they're valid or not. Right, there's a set of arbitrary quantum numbers defining an electron. Perhaps I should just turn on the lights a bit. It's a bit dark. Can everyone see that? All right, so there's a set of quantum numbers, N, L, ML, MS. N is the, like I said, using my analogy, the country, L is the city, ML is the street, MS is the street number. Yeah? So, is that a valid set of quantum numbers, yes or no? No, why not? ML cannot be plus 3 if L is plus 2, because if L is plus 2, it means that we're talking about a D subshell type, and then we can't have an ML plus 3 exactly. What else?
The string can only be plus or minus.
Correct. So this is invalid, and this is invalid. If n equals 3, L can be plus 2. That's allowed, right? Because we're in the third energy level. But this is not allowed. Right, so you got to, that's the sort of thing you've got to really understand intimately, is the relationship of these quantum numbers with respect to each other. Okay? So, I think now we're ready to move on, having looked at these very important preliminaries. We're now going to move on to the next topic. All right, so you see we're moving very quickly in this lecture. And this is something of paramount importance. In fact, I would go as far as to say that this is one of the most important things in first year chemistry. In fact, the most important. And in fact, it's something that every professional chemist uses. It is so important, I cannot stress it enough. Lewis structures. How to write down correctly the Lewis structure of a molecule, of an ion, and understand it. And I can tell you, I've encountered some PhD students that still can't write down decent Lewis structures, right? And that's what we're going to do. In this class, we're going to all learn how to write Lewis structures. In fact, the second PBL session is devoted to Lewis structures and electron geometry. It is super critically important. I think I've made my point. All right, let's look at this. What is this all about? Well, what we're talking about here is a way of understanding ultimately the shapes of molecules, that we can predict it by something called a Lewis structure. And this comes from a guy named Lewis. He was an American chemist. And he was the one that actually, I think he was American. He basically said, okay, chemistry is a phenomenon of valence electrons. We're not interested in the core electrons. What defines the reactivity and bonding patterns of atoms are only the valence electrons. In other words, the elements in the outer shells, in the outermost shell, which we get essentially from the electron configuration. So you see everything, chemistry, if one builds on the other. It's like mathematics. If you don't understand something, then, the house of cards collapses. So this is important. So he said, let's just consider the valence electrons. Now, before we get into that, I just want to draw your attention to something you probably already know. And that is that essentially bonds, any bond between chemical bond between two atoms, has always got covalent and ionic character. But it depends on the nature of the atom. Some will have a very large covalent character and almost no ionic character. For example, the bond between H2. And some will have a large ionic character. For example, sodium chloride. And that is dependent on the difference in electronegativity between those atoms. We're going to get to that right at the end of the lecture. Just bear in mind that we're dealing with ionic and covalent bonds. In the context of Lewis structures, however, we're only thinking about things in terms of covalence. All right? More or less. Okay. Now, the whole idea of a Lewis structure and drawing a Lewis structure of a molecule or an ion or some species is that all the atoms have 8 electrons around them. Why 8? Can someone tell me why 8? What's special about 8?
Noble gas?
Yes, it's noble gas configuration. Remember the periodic table I showed you right at the beginning? I said, in fact, let's look at that. In fact, I have one here. 8. Forget the numbers at the top, consider the numbers at the bottom. You see it goes to 8. And the reason why it goes to 8 is because it's the noble gas configuration, as you said. The noble gases, what it basically means, are happy. They're happy, they're quite happy on their own. They've got all the electrons. Their outer shell is full of electrons, and they sort of like these are not very social elements. They sort of float around as monoatomic entities. They want to be left alone, right? These elements here are very social. They want to form bonds. So you can think of atoms. Also, atoms and molecules have personalities. So these are not very social. These are quite social. These are also very social. So yeah, it's noble gas configuration. It's happy with its 8 electron. And what we're trying to do in a Lewis structure is make sure that all the atoms have 8 electrons around them. how do we draw a Lewis structure? Let's start off with the simplest molecule, hydrogen, H2. Now the way that we do it is we simply write down the identity of the atom, in this case H, and we represent the valence electrons with dots. Now hydrogen is in group 1, so it has one valence electron. Beryllium, magnesium, calcium, strontium, barium, radon. Group 2 would have 2 valence electrons. Forget about these for the moment, because incidentally, the model that we're discussing now, Lewis structures and writing Lewis structures, does not work with transition metals. With transition metals, if we want to understand and rationalize bonding, we have to turn to more advanced theories, like molecular orbital theory, crystal field theory, something that's not part of this course, that would be part of a more advanced course. In fact, I do discuss this in the follow-up course from this in the fall. We talk about transition metals. We're not talking about those now. But group 3, so boron, aluminium, gallium, indium, and thallium, these elements here would have how many valence electrons? 3, yes, because it's in group 3. Carbon, silicon, germanium, tin, and lead. 4 valence electrons, and so on. These have 8 valence electrons. They are already in their full closed, so-called closed shell configuration, and they're happy and they want to be left alone. You can get them to bond to other elements, but it takes some effort. They're very unsocial. Now, yeah. So let's get back to our example. Yeah, so here we have essentially these atoms, and what we do when we start drawing a Lewis structure for a molecule is we put all the atoms down and we put the valence electrons around it by dots. Very simple, and you get the number of valence electrons by figuring out what group in the periodic table these elements are in. Now, let's get to hydrogen. So hydrogen, it's in group 1. We want to make a bond between these two. Each has 1 electron, and that's basically how we do it. And we represent 2 dots between 2 atoms with a line, and that represents a covalent bond. The lines represent a covalent bond. Now, this is essentially the Lewis structure of hydrogen. Very simple. Now, we've got different types of electron pairs. We have bonding pairs, which we see here, but we also have lone pairs. Lone pairs are electrons that are not involved in bonding. Let's look at chlorine. Chlorine has 7 valence electrons. If I want to marry 2 chlorine atoms together, I basically take each of these unpaired electrons here and marry them together to form a covalent bond. And what I end up with here is this is the Lewis structure of diatomic chlorine gas. We have a bonding pair and lone pairs. Each chlorine atom has 3 sets of lone pairs. Lone pairs are electrons that are not involved in bonding. And what else do we see? We see that we have around each chlorine atom a total of 8 electrons. So each chlorine atom has achieved what we call noble gas configuration, and it's happy. Atoms want 8 electrons around them. Hydrogen cannot have 8 electrons around it. Why not?
There's only 1 electron.
Well, there's only 1 electron, but there's only 1 orbital, an s orbital.
Yeah, that can
That's
just do
the
2 on
maximum.
it.
Exactly. Right? Hydrogen doesn't even have, let's say, a second energy level. So, you know, that's all it can do, and then it's happy. Right? So, that's basically the departure point in Lewis structures. Now, let's look at something a little bit more complicated. Water, H2O. How do we do this? Well, oxygen has 6 valence electrons. Hydrogen has 1 valence electrons. We basically put it all together and we get something that looks like this, H2O. Notice, oxygen has how many valence electrons around it now in the molecule, in total? 8. So it's achieved noble gas configuration. The hydrogens are happy because they've each got 2, and the oxygen has 2 bonding pairs and 2 lone pairs. So in fact, the Lewis structure, so the Lewis structure of this, whoops, sorry, is, in fact we'd write it like this. Now, I leave it up to you, but you can write lone pairs, with 2 dots or with a line. So you can write it like this, or if you want, you can write it like that. So a line, just easier, represents a lone pair, right? 2 dots or a line. This is incidentally how, when I was teaching this in Germany, this is how we would do it. This is sort of the British way. Okay, now, how do we know which atom to put in the center? That's the next question. I mean, if I'm confronted with the formula H2O, how do I know that the H mustn't go in the middle? And the simple explanation is that generally, we put the most electropositive atom in the center. Right, more about that in a minute. We're going to now just do lots of examples. Right, here we have some guidelines. Hydrogen atoms are always terminal atoms. Central atoms are generally those with the lowest electronegativity. How do we know which atoms have the lowest electronegativity? Any ideas? Yes?
Closer they are to fluoride in the periodic.
There are trends in the periodic table. It's the subject of the first PBL session, right? From left to right, electronegativity increases. From top to bottom, it decreases. Stuff like that. So we can figure it out, sort of, from trends, periodic trends. Indeed, the halogens are the most electronegative, and fluorine is the most electronegative element, for example. Noble gases are electropositive because they've got noble gas configuration, essentially. So those always go in the middle, if you have a molecule bearing a noble gas. Carbon atoms are always central atoms. Generally, structures are compact and symmetrical. Basically meaning you're not going to put a row of atoms next to each other. You're going to try and put them around the central atom. We'll do some examples in a moment. Right, let's continue. These are some guidelines that I put here for you that you can review. Some people tend to have, need to have a step-by-step way of doing these Lewis structures. I don't particularly like that. The way that I write Lewis structures and the way that I teach it is that it's sort of like a game that one plays with, you know, mixing and matching electrons and moving things around until you get something that sort of works. I don't like the step-by-step approach, but that's just a matter of taste. If you want to, you can use this as a guide to drawing Lewis structures. It will be posted on the website, Ilio. All right. Let's now look at the situation where we're confronted with something like CO2. So the question is, what is the Lewis structure of CO2? Well, we start off with putting the most electropositive element in the center, which is carbon. Oxygen is more electronegative than carbon, so that's the starting point. Each atom gets its valence electrons. Oxygen has 6, carbon has 4. And now we've got to somehow marry these 3 atoms together in such a way that each atom has 8 electrons around it, so that they've achieved noble gas configuration, so that they're happy. How do we do that? Well, we sort of play a game. And what we do is it's okay, well, here we've got 2 unpaired electrons, and here we've got 2 unpaired electrons. It makes sense to marry those 2 together to make a bond. So I'll make a bond, a chemical bond, and then I have something like this. Now this is just a working model. Is this an acceptable Lewis structure, yes or no? Why not?
Because the carbon haven't achieved the 8 electrons.
Correct. Carbon has 2, 4, 6 electrons around it. That's no good. Carbon wants also to have 8 electrons. So what do? Well, it's very simple. We move Well, there's a number of ways you can do it. You can move things around. You can move all these dots around in the molecule as you wish, right? That's the point. So if you do it enough times, you sort of get very good with it. You just got to practice, practice, practice. Well, what we can do is, I mean, the way that I've represented the valence electrons here, you notice that I've got these two electrons here. These are sort of unpaired. Well, I can sort of, what can I do? I can marry these two together, and I can marry these two together here. And if I do that, I end up with the Lewis structure at the bottom here. Now, what I've basically got is I've got between this carbon and this oxygen essentially 4 shared electrons, and between this carbon and this oxygen another 4 shared electrons. And we write that with 2 lines, so it's a double bond. And is that an acceptable Lewis structure? Yes, because oxygen has 8 electrons, 2, 4, 6, 8. 2, 4, 6, 8, and carbon also has 8. They're all happy. They've all achieved noble gas configuration. That's the only thing you have to remember when you're writing Lewis structures. Let's get all the atoms to have at least noble gas configuration. There are exceptions to this, which we will look at in a moment. And I suggest we have a 5-minute recess. Yeah? Shall we continue, or you want a 5-minute break? Let's reconvene in 5 minutes. All right?